Hey guys, and welcome to this video on converting from hexadecimal to octal. So here we have our problem. We want to convert the hexadecimal number 17BA, which is of course base 16, to octal, which of course is base 8. And to the left here in green, I have a chart that maps a number, which is the number system you're most likely used to, the base 10 number system, digits from 0 to 9, and I'm mapping them to the binary representation of that number. So I only put numbers 1 through 12 here for the mapping of the binary numbers, and that's all that we're going to need for this video here. And the reason why I have this chart is because we're going to take that hexadecimal number, convert it into a binary digit, and then convert that into the base 8 number or octal. Okay, so let's go ahead and get started by first writing our hexadecimal number, which is 17BA. Okay, and like I said, we're going to take this number and convert it first to binary. So we are going to convert starting with the letter A. We're going to convert the letter A into a binary number, and A represents the number 10 in hexadecimal. So we go to our chart where we have the number 10, which is down here, and we look at the mapping from the number 10 to the binary digit, and we see that the binary digit representation of the number 10 is 1010. So here we're going to put 1010. Okay, and I'm going to erase that arrow. All right, next we're going to convert the letter B. And so B in hexadecimal represents the value or number 11. So we're going to go to our chart and look at the number 11. And we see that the binary digit representation of the number 11 is 1011. So here we're going to put 1011. Okay, and I'm going to get rid of that arrow. Next, we're going to convert the number 7 into a binary digit. So we go to our chart where we see the number 7, and we see that the binary representation of the number 7 is 0, 1, 1, 1. Okay? All right, and now I'm going to get rid of this arrow here. And last but not least, we're going to convert that number 1. So converting it into a binary number, we get we look at this number here, right? Look at the number 1 in the chart, and we see that the binary representation is 0001. So that's what we're going to put here, which is again 0001. All right. So pretty simple so far, but you'll notice that I chose 4 bits or 4 places to put a 0 or a 1. And the reason for this is because the most that a binary number can be, the best number or the greatest number that the binary digit can be represented by 4 bits is 1, 1, 1, 1. So that's the highest value that a binary digit can be. And what does this value equal? Well, this value is equal to the number 15 in our base 10 number system, or the normal number system that you're used to. And the smallest number that it can be is 0000, which of course represents the number 0 in base 10. So what that means is if we only have 4 bits, then our range of possible numbers or digits is 0 to 15. So that should sound familiar because base 16 are numbers from 0 to 15. And that's actually 16 different digits if you're counting from 0 to 15. All right. So that's why we have 4 bits there specifically. That's why we don't have like 5 bits or 10 bits or 20 bits. We only need 4. All right. Okay. So I just kind of want to explain that. And this here is, of course, binary or base 2. Okay. All right. So now what we're going to do is we're going to take these digits and we're going to we're going to make them 3-bit digits now instead of 4-bit digits. So let's go ahead and come down here, and we only want 3 of those bits. So we get 0, 1, 0. And then I will explain why we're only using 3 bits here when we're done. Okay. And so next we're going to take that 1 from over here, and we're going to take these 2 1s from over here, and we get 1, 1, 1. Okay. And then we're going to take the 1 and the 0 from over here and the 1 from over here, and we get 1, 1, 0. And then we're going to take the 0, 1, 1 from over here. So we get 0, 1, 1. And then we're going to take the 1, 0, 0 from over here. And so we're going to get 0, 0, 1. And we can technically take that leading digit 0 from right here. But if but when we have a leading digit that occupies the most significant digit, then they can be left blank. Okay, so we don't really need to do anything with that. All right. So now I told you guys earlier I was going to explain why we're using 3 bits now instead of 4 bits. Well, it's very similar to why we used the 4 bits before. So 3 bits can represent a digit in base 8. So the highest value that a 3-bit digit can be, a 3-bit binary digit can be, is 111. And what does that equal in base 10, or again the number system that you're most likely used to? Well, 111 is equal to the number 7. And the smallest number that this can be is 0, 0, 0, which is equal to 0 in our base 10 number system. So the possible range of values is 0 to 7, which are 8 different digits. And of course, octal can only go in that same range from 0 to 7. It never reaches that value 8, just like base 16 or hexadecimal never reaches that value 16. It's just numbers from 0 to 15. All right. Okay. So now what we can do, and actually before we do that, I guess I should put this right here is binary as well. But it's like the representation of octal in binary. Okay. So what we can do is we can take these digits now and we can translate them by using this map over here to the left in green, just like we did earlier. So now we can map these binary digits to the number value. So let's take a look at 0, 1, 0. And we go over here to our chart to the left. We're going to look for 0, 1, 0. So 0, 1, 0. Let's see where you're at. 0, 1, 0 is the number 2 there. And you may say, but That's not 0, 1, 0. That's 0, 0, 1, 0. Again, that leading 0 in the significant digit can be left blank. So we can represent that as 0, 1, 0 or as 1, 0 if we wanted to. But here we're using 3 bits, so we're going to represent it as 0, 1, 0. Okay? All right. So here we put the number 2. Then we look again to the chart to the left for the binary digit 111, and we see that here. And that is just the number 7. So we're going to put 7 here. And next we're going to look at the binary digit 110. So 110 is here. Okay. And that's the value 6. So we're going to put 6 here. And then we have 011. So 011 is, let's look, here it is. It's the binary digit 3. It is the number 3 in base 10. So 011, which is the binary digit, is the number 3 in base 10. So sorry about that, mixing up my words. So here we're going to put the number 3. And then we have 001, which of course is just 1 in base 10. All right, so we're going to put the number 1. So now what does this mean? This means that our hexadecimal number, which is 17BA, and we just put a little subscript here for base 16, is equal to 13672 in octal, or base 8. So for that, we just put a little subscript of 8. And that is our answer. So I hope you guys enjoyed this method of converting hexadecimal to octal. And I hope my explanation was pretty clear. So thank you guys for watching this video. Please leave any questions you have in the comment section. Let me know if I made any mistakes or any videos that you'd like for me to put up on my channel. And if you like this video, please click that like button and that subscribe button. And if you found it helpful, please share it. Maybe others will find it helpful as well. And as always, guys, thanks for watching, and I will see you all